Welcome to the Kinetics and Equilibrium Review. Before we get started, let's talk about the makeup of the test, and it is all multiple choice, so I know you'll be excited about that. So let's get going. Just like always, you need to know your vocab. That is something that tends to stump you guys on tests, so make sure you look at your vocab. If you haven't already done it for your Parker Points or KimCash, make sure you get that done. And these are some ones that you really need to pay attention to. The one that I want to talk about just very quickly is rate, because it's defined a little bit different. And so it's just basically how fast something changes with time. So how fast So the rest of those you can be looking up. Make sure you know what an intermediate is. Remember, an intermediate appears in one step of the reaction mechanism and then disappears, so it doesn't appear in the overall equation. Make sure you know reaction mechanism. Homogeneous means all the same phases. So make sure you understand all those definitions and make sure you look over those before the test. All right, what is required for a collision? Remember, for a collision to be effective, the particles, first of all, they have to collide, and they have to have sufficient energy, and they have to have proper orientation. So in your notes, we talked about that, so make sure you know that those three things happen. Without collisions, we wouldn't have any reactions, and anything that we can do to increase the amount of collisions will increase the amount of reaction that can take place. Next question, what takes place in an activated complex? Remember, that always shows up at the top of the peak when we're looking at an energy diagram. And what happens is, first of all, the bonds have to break, which are the reactants. And if you recall from the notes, that means it is an endothermic when the bonds break. And then the new bonds have to form, and that's your products. And remember, when new bonds form, that is always exothermic. Depending on which one had the greater energy, will determine whether the overall reaction is endothermic or exothermic. And then the third question on this slide, what does raising the temperature of a system result in? We talked about it in class. If you heat them up, you speed them up. So anytime I increase the temperature, it means my particles are moving faster. Also means the kinetic energy is increasing. And so when this happens, we would have more collisions. And when we have more collisions, we have a higher reaction rate. Also, because their kinetic energy is increasing, then also there's more effective collisions that have enough energy to make that collision effective. So this next question is kind of a repeated question within an activated complex. Do bonds break, form, or both? And of course it's both. If you need to see back at question 2, go back and look at that. Then we have what is used to speed up a chemical reaction. And remember, when we're speeding up a chemical reaction, that is a catalyst. The catalyst will speed it up by lowering the activation energy. And I need to make sure you understand that when we have a catalyst, it is not being used up in the reaction. We actually could reuse that catalyst. A lot of times it'll be cleaned up and regenerated and can be reused, which makes it cost efficient when you're doing it in production of manufacturing facilities. And then the last question on this slide, what is used to slow down a chemical reaction, which is like the opposite of a catalyst, and that is inhibitors. And they slow down the reaction, and they're slowing it down by increasing the activation energy. Remember, EA stands for activation energy, whereas the catalyst lowered it. They lowered the EA. So that's the difference between the two. Some examples of why you would want to lower or slow down a reaction rate, things like corrosion. We want that to happen very slowly. And we talked about in class food spoilage. I wouldn't want to leave my leftovers out overnight because they would go bad. So I put them in the refrigerator, and the temperature being cooled down inhibits the food spoiling as quickly. Next question is, why are catalysts beneficial? And of course, it's because they allow the reaction to happen faster. In terms of chemical plants, it also allows them to make the product faster, which means the more product they can make, the more money they can make. If you have the next question, if you have crushed sugar versus cube sugar, which will happen at a faster reaction rate? And of course, common sense and our real world experiences, we know that crushed sugar or granulated sugar, like what we're used to using on our cereal or in our tea or coffee, it has a larger surface area than a sugar cube, and so it would dissolve faster or react faster. And then the last one on this slide, if you have 1 molar HCl versus 6 molar, which would have a faster reaction rate, and of course the 6 molar would, it's a higher concentration, which means it has more solute, which for more particles, and of course more particles mean you have more chance of collisions, and so that would make you have a faster rate. So this question says name 3 things that affect reaction rates. And although you only have to name 3, it's a good idea to know all 6. First one is concentration, which we just talked about. Higher concentration means a higher reaction rate. Nature of reactants, we talked about that in the notes. Remember, group 1 and 2 metals are highly reactive metals, and so their nature is that they would be very reactive, and so they would have a higher reaction rate, say, than something like silver or gold. Temperature, we talked about that also already. Higher temperature means faster particles with more kinetic energy, which gives you a higher chance of effective collisions. Surface area, we just talked about in the previous question. Larger surface area, rather, means more particles to react. And then, of course, catalyst would speed up a reaction rate, and the inhibitor would slow the reaction rate down. The next question says, what symbol represents equilibrium? We can show that in a couple of ways, but usually there's some sort of double arrow. This one is one way, where it's one arrow with the double headed on. Sometimes you show 2 individual ones like these, or different ways you can show that. But you need to be able to recognize if it's in equilibrium, both the forward and the reverse reaction are happening at the same rate. And it seems like at equilibrium, sometimes it seems like nothing's happened, but it is a very dynamic situation. It's just happening on the molecular level. And so you may not necessarily, sorry about that, I was going too fast. You may not necessarily see the changes happening, but you have the forward and the reverse reaction happening at the same rate. All right, in these 2 questions, they want you to draw the potential energy diagram for both an endothermic and an exothermic, label the reactants, products, and the activation energy, and then it wants you to tell them how their energy of the reactants, products, and the activation energy compares with each other. And of course, I want you to recall that EA, when we write it like that, is how we write activation energy. So remember, in an let's do endothermic first. In an endothermic reaction, the energy is being absorbed. And so our products are going to have more energy than the reactants because they absorbed energy during the reaction. And the way we always show activation energy is always from the reactants to the top of the peak in both of these, reactants to the top of the peak. And so this right here would be your activation energy. So in terms of the energy in relationship to each other, the reactants have less energy than the products, and the products have less energy than the activation energy. So it's completely the opposite when we go to exothermic. Because exothermic is releasing energy, our products have less energy than the reactants because energy was released. Again, activation energy is from the energy level of the reactants to the top of the peak. And so this time our products have less energy than our reactants, and our reactants have less energy than our activation energy. All right, let's move on to the next slide. Now talking about equilibrium a little bit, wants to know what a reversible reaction is. And that is a reaction that can both run forward to the right, that means towards the products, and it can also run left, meaning the products could go back towards the reactants. And then it says, how does the rate for the forward and reverse reaction compare at equilibrium? We talked about that just a few minutes ago, and they are equal at equilibrium, meaning the forward and the reverse reaction are happening not only at the same time, but at the same rate. And so I want y'all to remember that under the right conditions, most reactions can be reversible. So the vast majority of reactions are reversible. All right, last few questions. This is a very short review, probably the shortest one we've done so far. Last one says, what kind of things will stress a system at equilibrium, causing it to shift, meaning go towards the products or go towards the reactants. And so the three things that can affect that is change in temperature, concentration, and pressure. Probably should have put a comma in there. Temperature, pressure, and concentration. Now, so let's look at this reaction. We've got A plus B going to C. It is showing the double-headed arrow there, and so it is a reversible reaction. Remember, when we see heat in a reaction, depending on where it is, it's either going to be an exothermic or endothermic. Because this is in the products, that means heat was released. And so if heat was released, it is exothermic, okay? And when we have heat in an equation, we treat it as either a reactant or a product. And so in this case, it's going to be treated as a product. And that's going to come into play whenever we look at the way things shift, okay? So here we go. Let's do the first one, decrease in the concentration of C. That means right here, C, we would decrease it, so we would be removing it. And if we are going to remove it, then our reaction would shift towards the right to make more product because we were removing part of C, so it's going to shift to the right. Next one was add heat. And remember, we're going to treat heat as a product. And so if we're adding to this right here, that means it's going to shift away from what we're adding, so it would shift to the left and back towards reactants, meaning it would start making more reactants. The third one says increase in concentration A. So if we're starting to increase A, we're adding to it. Again, remember, it's going to shift away from the side of the stress, and by adding concentration, we're stressing the equilibrium, so it's going to shift away from where that stress is being added, so it's going to shift to the right towards making more products. Okay, and then the last one is increase in pressure. An increase in pressure is treated a little bit differently, okay? Whichever side of the equation has the least number of moles or the fewest number of moles, that's where it's going to shift towards. And so this side has 4, this side only has 3. And so when I increase the pressure, what's going to happen is this is going to shift this direction towards the left, so it would make more reactants. If you are still having trouble with that, you might want to look at some of the examples in the book or go back and look at the worksheet we did in class to try to understand that shift in equilibrium. Remember, that's called Le Chatelier's principle that says a system will adjust itself in order to accommodate the stress that's being added to it. All right, that's the end of this review. I wish you luck on the test. This is the second to last one. We're almost there, guys and gals. Stay tuned for the jokes. All right, here we go with joke time. First joke. What prize do you get for putting your phone on silent? The Nobel Prize. What kind of key doesn't open a lock? A monkey. And the last one. What kind of tea is hard to swallow? Reality. All right, see you in class. Have a good evening.